Hi, everybody. In this lecture, we're going to begin a discussion of waves. So to launch us off, there's two kinds of waves in classical physics, two main types. Those are mechanical waves, and those require some kind of physical medium to be disturbed. Some examples of mechanical waves are waves on a string or sound. And in a mechanical wave, the wave is the propagation of a disturbance through a medium. So for example, for a wave on a string, you get the string moving up and down. And in a sound wave, you've basically got a pressure wave. Now, there's another kind of wave, and they don't require a medium. And those are electromagnetic waves or light. In those, no medium is required. So of course, light can travel through the vacuum of space. And some examples of that are light waves or visible light, radio waves, X-rays, things like that. Okay, in this lecture, we're going to focus more in on mechanical waves, which require a medium. And we might get to light waves later in this semester. But for now, in the images here, you can see a water wave where you have some kind of disturbance, maybe a rock thrown in the pond or something like that. And then that disturbance spreads out in a circle from where it goes as time goes on, and the wave propagates through the water. And then in the lower picture, you can see a wave on a string. So there you had a hand grabbing the string and wiggling it up and down in a sinusoidal fashion. And then that caused a wave on that string to move to the right, for example. So in both of these cases, there's a medium. In the top example, it's the water. And in the bottom example, it's the string. And the wave travels through the medium. For both of these waves, the particles of the medium don't really move. They just wiggle up and down. So in other words, you're not transferring matter over a distance for mechanical waves, not necessarily. What you're doing is making the medium move up and down. So it's the disturbance that travels and not matter. Now, one thing that all waves do transport is energy, however. The disturbance itself, the wiggling of the medium, is a form of kinetic energy, and it's that wiggle that moves, and so it's the energy that's transported. And as an example here, you can see you had put some kinetic energy into the string on the left-hand side by wiggling that up and down, and then that disturbance or that wave pulse travels to the right, okay? So this is the case with continuous waves in media. They begin with a vibration, and then they're transmitted through internal forces in the medium, okay? And lots of times we're going to use sinusoidal waves as a model, although waves can be in more complex shapes than that. That's a little bit beyond the scope of this course. Now, all waves carry energy, even electromagnetic waves that don't have a medium. So I just want to emphasize that. It's just the mechanism for carrying the energy that differs. So, for example, light is an oscillation of an electromagnetic field. And then sound, which we'll talk more about later, is a pressure wave. Now, we can also group waves into the categories of transverse waves and longitudinal waves. So let's talk about transverse waves first. This is a picture here on the right of that wave on a string, which I've showed before. And if you have a traveling wave or a pulse that causes the oscillation perpendicular to the direction of propagation, then that's a transverse wave. So waves on a string, for example, like here, are often transverse waves. Light is another example of a transverse wave. And what I mean by this is that in this example here in the picture, the rope gets displaced upwards and downwards, maybe if it's wiggling back and forth. So that's what we call the direction of oscillation. In this picture, it would be up and down is the direction of oscillation. But you can see that the crest of that wave, that disturbance, is moving in the direction of the red arrow to the right. And that's what we call the direction of propagation, okay? And so here, up, down is perpendicular to right, okay? And so the direction of oscillation is perpendicular to the direction of propagation. And that's a characteristic of transverse waves. Now, we can also talk about longitudinal waves. If you have a traveling wave or a pulse that causes an oscillation that's parallel to the direction of propagation, then that's a longitudinal wave. And in this picture here, you have a slinky, for example, and the slinky gets, you give a push to the slinky, right, along the direction that the slinky stretches, and that'll cause the coils of the slinky to alternately compress and stretch as the wave goes through, okay? So that's one example of a longitudinal wave. Another common example of a longitudinal wave is sound, which is a pressure wave, and we'll talk more about that later. Okay, let's discuss some of the terminology that we're going to use when we talk about waves and their characteristics. So first of all, we're going to talk about the amplitude of the wave. And the amplitude of the wave is the max displacement of the oscillation of the wave from equilibrium. Okay, so in this picture here below, I'm going to call equilibrium the media when it's not being disturbed by the wave, okay? And here, that's indicated with the black line that runs through the middle of this red wave. That's the equilibrium position of the medium. And you can imagine that maybe this is a snapshot of a wave on a string or a water wave, for example, okay? Now, the amplitude is the absolute value of the max displacement of the wave from equilibrium. And so here, the amplitude is the distance between the black line and the crest of the wave, or the black line and the trough of the wave, and they should be the same there. Okay, so that's the amplitude of the oscillation of the wave. Now, the next piece of jargon I want to throw at you is wavelength. Okay, so the wavelength is often symbolized in many texts by the Greek letter lambda, and the wavelength is how long the wave is. Or to put it another way, it's the distance between the same point on the wave, for example, peak to peak, or trough to trough. Or you could pick some other random point on the wave like is done here, okay? And it would be that same point on the wave at the next wave, okay? So that's the distance or length of a single wave, right? So that's our wavelength. Now, another thing that we talk about a lot is the frequency and the period of the wave. So the period is the time that it takes for one full oscillation of the wave to pass through. So let's say that you're sitting there watching a water wave pass by, okay, and you've got a stopwatch or something. And so you are looking at a point right in front of you, you're in the ocean or something, and there's some waves rolling in. And so you start your timer when this crest of the wave starts, and then you stop your timer when the next crest reaches you. And that would be your period, okay? Now, 1 over the period, or the frequency, okay, is the number of oscillations per second. We often use f, lowercase f, to symbolize the frequency. So another way to measure the frequency, let's say that you want to measure the frequency of the period of the wave. Another way to do it would be to stand in the same place in the water and start your stopwatch and then count the number of crests that pass your position at some given time. So you count maybe for a full minute or something, and you count the number of crests that passed your point for that entire minute. And then you would divide that by 60 seconds, and that would give you the frequency, right? And so, for example, if you stood there for a full minute and counted 3 crests, right, that passed you, then your frequency would be 3 divided by 60 seconds. Okay, so that would be your frequency. Another way to put it would be that the period would be that each wave came along every 20 seconds. If you stood there for a minute and you counted 3 waves, then that would be, you know, a period of 20 seconds. So either one of these two things, and they're related to one another by the frequency is 1 over the period. Now, talking about SI units for these things, amplitudes and wavelengths are distances, and so they would have SI units of meters. The period is a time, so it would have the SI unit of a second, and the frequency is 1 over a time. So the SI unit of that would be 1 over a second, which is often called a hertz. That's symbolized by a capital H and a lowercase z. So 1 hertz is the SI unit of frequency, which is 1 inverse second. Now we have an equation that relates some of these quantities. If you want to measure the speed or the velocity of a wave, then you can set that speed or velocity of the wave equal to the wavelength times the frequency, or alternatively, if you like to think of it that way, the wavelength divided by the period, okay? Now this makes sense. The speed of the wave it would travel a distance, wavelength lambda, in one period, right? And so if you think of a speed as a distance divided by a time, then the distance would be the wavelength and the time would be the period. So lambda over t, which is also equal to lambda f, and that gives you the speed of the wave, okay? So that's some of the terminology that we're going to use and some of the equations that we're going to use to describe waves. Okay, let's do a quick set of example problems here. Okay, so here is a snapshot of a wave at a given time. And so you see the sinusoidal looking thing. And on the y-axis, that's the displacement of the wave from equilibrium. And then the x-axis, maybe this is a snapshot or of a water wave or a wave on the string. And this shows you where the crests and troughs are for that wave. Okay, so what's the amplitude of the wave in the snapshot? Well, here, remember the equilibrium is indicated by the horizontal line, which is the disturbance of the medium from its equilibrium position would be the wave that goes like this, okay? So remember that the amplitude is the max displacement of the wave from equilibrium. And so you would look at either the crest or the trough of the wave here, the up or the bottom part of the wave, and you would see how far it is from equilibrium to that. And so to me, from this sketch, it's kind of an estimate still, but there you go. It would look like about 0.1 meters. And so for me, that would be answer B, okay? Now, also it's asking, what is the wavelength of the wave, okay? All right, well, if you go from corresponding points on nearby or neighboring waves, you could start here, right? And that's the beginning of the wave. And then it goes up and down one full time, and then we're back here. Okay, so the wavelength of this wave is 0.2 meters, okay? So that would be answer C for the second one. All right, now next, number 3, if the frequency of the wave is 120 hertz, then what's the wave speed? Okay, well, in the previous problem, number 2, we figured out the wavelength of the wave, which was 0.2 meters. So now we can say the frequency of the wave is 120 hertz, F equals 120. And then we can use our equation V is equal to lambda F and multiply 0.2 meters times 120 hertz, and we get the speed of the wave, which is 24 meters per second. All right. A little bit more about wave speed. The speed of the wave depends on the physical characteristics of the medium. So for example, the speed of light in a vacuum is always the same. It's 3 times 10 to the 8th meters per second. But if you pass light through a material, then the speed of light will drop. The amount it will drop is by the index of refraction n, okay? So that tells you that the medium helps dictate wave speed. We're going to talk more about this in a coming lecture, but the speed of sound in a medium depends on the density of the medium and also the temperature of the medium. So those are some characteristics of the medium, all right? The one I want to introduce in this lecture, though, is a simple equation for waves on a string. And this is important in things like musical instruments like guitars and pianos, for example. So for a wave on a string, the equation that describes the speed is equal to the square root of the force of tension in the string divided by the mass per unit length of the string, which here I've called mu, okay? For force of tension, I've used F for force and the little subscript T for tension. So what this tells us is that when the tension is greater, the velocity is greater, since each segment of the cord is in tighter contact with its neighbor. And the greater the mass per unit length, or the fatter, if you will, or denser the string is, the more inertia the cord has, and the more slowly the wave will propagate through the medium. And of course, this is really readily apparent in a guitar. You tune a guitar by changing the tension in the strings, right? You pull them tighter or make them looser to get them to the frequency or pitch that you want. And the strings have different thicknesses to achieve different notes. You can see that you've got a thick string here on the left and a thin string here on the right. And they get thinner as you go right, and that gives you different notes or pitches, okay? All right. Now we talked about how waves transport energy. What kind of equations and what kind of descriptions can we put to that idea? So just as the oscillation that starts it kind of gives you an indicator of how much energy, right? And let's say that, for example, you wanted to pluck a note on a guitar string and you wanted to make it louder, you would pluck it harder, right? So with that kind of idea, the energy transported by the wave is proportional to the square of the amplitude of the wave. If you want a little bit more chilling example of that, you could take a look at this image of a tsunami here on the right, right? So tsunamis have really high amplitudes of oscillation of the medium, and that's what makes them so dangerous. The higher amplitude of oscillation means that they have a lot more energy, and that has the ability to do some really destructive work on all the buildings and people in its path. And you wouldn't get this upset about just a little ripple wave or a normal wave rolling into the beach that's maybe only a meter or two tall, but something like this would scare the heck out of you, right? Okay, so here we have the definition of an intensity. An intensity is the amount of energy per unit time per unit area that a wave transports. Now, an energy per unit time is a power, so we often say that an intense wave has a lot of power per unit area. So if you put a lot of power into a smaller area, it's more intense, or if you put a lot more energy per unit time, then you have a more intense wave. Now, if a wave is able to spread out three-dimensionally from its source and the medium is uniform, then the wave is spherical. Now, before you think that that's a silly example or a silly thing to do, you can think of the fact that, like, if you pluck the string on a guitar, then the sound will move outward from the guitar string, right, and go outward. And it goes up and down and left and right and front and back equally. So that would be one example of a spherical wave. Now, just from geometric considerations, you can see that as long as the power output is constant, that the intensity of the wave would die off as 1 over the distance from the source of the wave squared, okay? And that's because the area, the surface area of a sphere is 4 pi r squared. So if you take the same power and distribute it over this area, right, then it gets less intense the further away you get, proportional to the inverse square of the distance, right? Now, for a perfectly spherical wave, the intensity is given by the power at the source, okay, at the origin here, for example, divided by the surface area of the sphere, which is 4 pi r squared. Let me do an example problem for that, okay? Let's say that you have a traditional 100-watt light bulb, and it produces about 5 watts of visible light. And the other 95 watts in traditional light bulbs are lost as heat and infrared radiation. And that's why LEDs are better than incandescents, because they don't really have that issue. But that's a different topic. So what's the intensity of the light on a wall 2 meters away from the light bulb? Okay, so the way that you would do this is you would assume that you have a spherical wave here. And so the power at the source that goes into the light would be divided by 4 pi r squared, assuming that all of that power at the source gets distributed over a sphere. Okay, so we take our power at the source that went into the light, which is 5 watts, as it says here in the problem. And then we divide by 4 pi r squared, where r is the distance away from the source that you are, here 2 meters. So 5 watts divided by 4 pi times 2 meters squared gives you, when you plug it into your calculator, about 0.1 watts per square meter. So that kind of gives you an idea of how fast the intensity can decay off as you get further away from the source. Okay, I hope that all made sense, and I'll see you in the next lecture.